So Leonardo da Vinci proposed a flying machine that would be able to work via corkscrew. He never actually made it, but he did draw it out. And this is able to move upwards with a constant speed of 2.5 meters per second. For ACE, as well as any class, power is equal to a lot of things. It is equal to your change in energy divided by time. It is also equal to force times distance divided by time. But more importantly, and more common, especially for ACE, it is force times velocity. Okay? So force times velocity would be the better one for that. Eventually, we're going to get it. There we go. So in this case, we have the velocity. That's easy. The force is not going to be 120 because if we think about it, the force of the device, I don't even know what to call it, the force of the air machine, must be equal to the force of gravity for them to be moving at a constant speed. With that in mind, that means that we have to do 120 times 9.81 because that's what the force of gravity is, times the velocity of 2.5. And if you do that, you will get an answer of roughly 2,900. It's actually 2,943, which ACE will follow conventional rounding in terms of significant figures. This had 1, 2 sig figs. This had 1, 2 sig figs, which is why the answer had 1, 2 sig figs. Don't overthink it. Even if it's not multiple choice, you can still get credit for the full unrounded answer. Hooray. All right. This one could be on any given test, not just an ACE test. 20 is one of the unique questions that you'll probably never see again, but you never know. Gravitational potential energy, if you have a parachutist falling at terminal velocity. If it's falling at terminal velocity, that means velocity is constant. And that would also mean that your force drag is equal to your force of gravity. Those two would be equal. Well, if your velocity is constant, that means that kinetic energy also has to be constant because kinetic energy is 1/2 mv squared. And if kinetic energy is constant, then we have a lot of issues with this answer. We're looking for one not correct answer. One not correct answer. And I'm going to find the one that's absolutely not correct in the beginning, and it's B, and I'm going to explain why the other ones are correct. So gravitational potential energy is converted into kinetic energy of the parachutist. His velocity is constant, which means his kinetic energy has to be constant. But then you might also be asking, what about this one says kinetic energy of what? The air. The parachutist moving through the air is going to move the air. It's going to put a force on the air, and the air molecules themselves will gain that energy and speed up. And due to the fact that the molecules speed up, the kinetic energy of the air itself would speed up, and therefore that is correct. Which is not why we didn't pick it, because we want to find the one's incorrect. The gravitational potential energy is converted to thermal energy. That one's more believable. Friction makes things hot. And thermal energy makes the parachutist hot, even though he would probably be cold up there in the sky. It's a lot colder up there. Number 5. Definitely out of order. We got a ball projected vertically downward. This is not energy. This is just a review of kinematics. So ball projected downward. Initial velocity 20 meters per second. Air resistance negligible. We got a delta y, or delta x, is equal to vi times t, 1/2 at squared. We want to know the displacement of the ball in a time of 1.5 seconds. The trick here is the velocity was down. It was thrown down, so negative 20, 1.5, 1/2, negative 9.81, 1.5 quantity squared. If you do that, you get 41. Ta-da. You get close to 41. Number 6 is a unique question. I like number 6 a lot more than number 5 because it talks about light and kinematics. So we have a light wave, which that is the actual symbol for a photon of light, is going towards a wall which is 150 meters away. There's the wall. It's going to hit the wall, and it's going to bounce back. And then they measure the total time that it will take for it to get back, and we need to know what that total time would be. Well, how far did the light go if it went 150 there and 150 back? 300. Okay? So 300 would equal velocity times time. And you may not know it, but the speed of light is constant. It does not change in air unless it runs into a wall or something. Then it stops. It reflects and does some weird stuff. But on your formula sheet provided to you would tell you that the speed of light is 3 times 10 to the 8th. You might not know it now, but you will know it by the time you get finished with the physics course because it gets used a lot. So if we divide 300 by 3 times 10 to the 8th, you get a time of 1 times 10 to the negative 6, which would rule out A, because that's a 0.5, and it would rule out C, because that's a 0.5. And it would not rule out B or D, unless you know what this little n and what this little m stand for. N stands for nano, and nano is 10 to the negative 9. Little mu stands for micro, so this would be 1 times 10 to the negative 6. Micro stands for negative 6. We got 10 negative 6. That makes it D. Moving right along. We got power. If it asks for definition, it is as simple as you can get. Just state any of the formulas for power, and you'd be good to go. Power is force multiplied with a constant velocity. Or you could say the work divided by time. Both of those would be fine. I think that the answer that is actually provided is work divided by time, but power is one of the few formulas that has a lot. Anytime you have a define, all they want is the word version of the formula. So that is easy points. If it's a 2-pointer, be careful, because it's normally not worth that many points. Speaking of which, we have an electric car. The electric car is moving 35 meters per second. It has a resistive force of 1750. Calculate the power transmitted by the wheels. Don't overthink it. Power is either force times distance divided by time or force times velocity. Do we have a distance or a velocity or a time? We have a velocity, which means hopefully we have a force, which we do, 1750. 1750 times velocity. We get our answer right away, and that answer is 61250 watts, which if you wanted to, on the mark scheme, it would have said 61,000. It would not have written the 250 because, actually, no, it would have. It would have written some of it. It wouldn't have written the 50 because this has 1, 2, 3 sig figs, but you get credit for either one. If it is a 2-point problem, you normally get credit for the formula and the plugging in the formula, and then you get 1 point for the actual answer. And so far, everything I've ever seen, even though they say you should have sig figs, they never actually put it in the mark scheme as a down mark if you don't. So you could write the full answer and not worry about it too much. Calculate the useful work by the motor as it travels 17 kilometers. Well, let's see. Well, the work is just force times distance, right? How much force is the car feeling? 1750. What would be the distance? 17 kilometers, which is 17,000 meters. And that is probably why it's worth a 2-pointers, because force times distance doesn't feel like it'd be worth 2 points, but knowing that you have to convert the 17,000 is probably worth 2 points. And this is a huge number. It's 297,512,340 zeros. Well, you've driven for 17 kilometers. It's going to be a lot of energy to drive 17 kilometers. I don't know if you've ever ridden or ran a 5K. That I get tired after that. All right. Now, the car is moving. The car is moving downhill. The car continues moving at the same speed. State and explain if anything has changed with the air resistance. Air resistance, we learned a little while ago, is proportional, which you could write determined by velocity squared. So because air resistance is determined by velocity squared, have we changed the velocity? No. Velocity the same? So air resistance will be the same. Ta-da. Don't overthink it. Where are we? Oh, we're at the easier problem. Well, this one's easier. We just need to put a check mark next to which ones are vectors, which ones are not vectors. I bet AICE would be really annoying with the mark scheme with this. If you don't get them all, you're probably not going to get any points. But is acceleration a scalar or a vector? It is a vector. You have to have a magnitude and a direction for acceleration. Displacement is the vector. Position is the scalar, or distance is the scalar. Gravitational potential energy. It can be positive, it can be negative, but does it tell you which direction it's going? No. So that means it's scalar. Speed is the scalar version of velocity. Temperature, even though it can be positive or negative, if you have a negative 5 degrees, that doesn't tell you if it's about to get colder or if it's about to get hotter. It just tells you it's negative 5, so that is also a scalar. Constant resultant force on a car. Blah, 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 blah. A lot of reading. Use the concept of work to show that kinetic energy is equal to this equation. There's a few keys here that we need to pay attention to. First, 3 points. It's going to be hard. Second, work. Okay, so we're going to prove that work is equal to 1/2 mv squared. So we need to start with work is equal to 1/2 mv squared. Work is force times distance, or delta x. So that means that we would need to do force times delta x is equal to 1/2 mv squared, which it's definitely not equal to 1/2 mv squared yet. We're not even close. But what can we turn force into? Mass times acceleration times delta x is equal to 1/2 mv squared. We're a little closer. You know why? Because we both have a mass now. All right, we got an issue now because we need to either convert acceleration or x, and I think that we're going to convert acceleration just because I think that it will work. And this thing started from rest and then reached a speed of v after a displacement, which they don't call displacement x, they call it s, which as we get closer to the AICE exam, I will do that as well. So I think we're going to use this equation, velocity final squared, velocity initial squared, plus 2a delta x. Velocity final is going to be just v. Velocity initial would be 0 because it started with rest. So velocity final squared is equal to 0 squared, 2a delta x. All right. Could I solve for acceleration? Absolutely. I could do that. Velocity final squared, divide by 2 and by delta x would equal a. Instead of writing a, I could write that in for a. I could substitute it in. So that would mean that we would have mass times velocity final squared over 2 delta x times delta x. What happens with the delta x's? They cancel. And we're left with mass velocity squared over 2. You don't need to write the f. Is that the same thing as 1/2 mv squared? Yes, it is. Mass times velocity squared divided by 2 is the same thing as mass times velocity squared times 1/2. So we did it. We did it. Woo! All right. That one's the hardest one on the entire paper by a long shot. It is unlikely you would get all the points, but that's okay. You can maybe get something. And that's okay. You don't have to get full points on these. You're trying to get half. Half or better is passing. That's the goal. Pass. All right. A one-pointer. We definitely have a chance for a one-pointer. Calculate the kinetic energy. Kinetic energy is just 1/2 mv squared. Hopefully we have an m and a v. We have an m. Do we have a v? Yes, we do. 17. Type it in. 920 times 0.5 times 17 squared is 132940. 132940. 132940. Okay? And then another three-pointer. This three-pointer is not hard mathematically. It is hard in terms of physics. So it says between the time of 0 and 5.8, we were speeding up. It wants to know the average power output during this period of time. Power is either equal to force times distance divided by time, or force times velocity, or it could be change in energy divided by time. Do we have any forces provided? Be careful, because like you might think you do, it says resistive forces is this, but it's the work done by resistive forces is that. This is a change in energy, not a force. How do we know we're speeding up? Because it's the same problem that said we sped up from rest to the 17 meters per second. Okay? So we have the work done against resistive forces that is this, which is kind of like the friction. We also have the kinetic energy that we gained from the previous problem, the 13,002, blah, 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 all that stuff, the 132940, 132,000. So what did the engine have to do? The power of the engine had to get us to speed up, so it had to gain that kinetic energy. What else did the power of the engine have to do? Well, it also had to deal with and overcome the resistive work non-conservative due to the air resistive and that resistive forces. So it had to gain kinetic energy, and while doing so, it still had to overcome the friction. So it had to do both, which is weird because friction is not going to be negative. It's going to be work that the engine had to overcome. So we really just have to add the answer from the last time, the kinetic energy that we had from the last time, that kinetic energy, and the work done that friction slowed us down by, and we divide by time. Change in energy divided by time. If you do that, you get something close to 3.1 times 10 to the fourth. So again, our engine had to gain us that kinetic energy and overcome the forces of a work of resistive energy, and then we divide by time. Whew. After 5.8 seconds, the speed becomes constant, so we're no longer speeding up. If we're no longer speeding up, do we have to continue to gain kinetic energy? No. So we now no need to gain kinetic energy, which means we're just going to have to deal with this air resistance part. If you're only having to deal with the air resistance part, are we going to have a greater or less than power? We won't need as much power. So we will have less power output due to the fact, I don't think we need to write this many words, that now the engine will not need to have extra energy for gain of kinetic energy and only have the work / power for, oh boy, resistive forces. There's probably a whole lot less words we could have written for that, clearly. And that is going to do it for this one.